Okay, let's go ahead and get started. So today we're going to review pointers and different memory. This hopefully is a review for y'all, but we'll review it from at least a C++ standpoint.
Just remind me.
I was asking my brother for help on my Perl homework, and he has never used Perl or C++, and he just graduated college with a computer science degree.
Where? Yeah.
Coastal.
Okay, well.
Don't go there for your degree.
All right, well, my opinion of them has
Drop.
I think he used like a
changed.
little bit of C++, but he said he mostly used like Java and JavaScript.
Wow. All right, anyways.
Graduated from.
Coastal.
So we're going to go over pointers again, and then we're going to go do a review of arrays, testing, and then we're going to go over your lab for arrays, which is just a review, and then we'll go over your first project.
Woo!
Yeah!
Super exciting.
All right.
Wish it wasn't long.
So static, and heap. Everyone here took Java from me, right?
Yes.
Okay,
Yeah.
good.
Yeah.
So static is fixed and static. Fixed size, I should say.
No way.
And static. The stack, that has to do with your function calls and increases and decreases as your functions are being called. So it allocates and deallocates. And then the heap is dynamically out storage. So in Java, what was allocated on the heap?
Objects.
Objects, right. And are you knitting?
Crochet.
You're crocheting. Oh,
We
cool.
discussed this last semester.
I'm so sorry.
She's
My
making a
apologies.
cupcake hat last semester.
Yeah.
All right.
Grandma.
So what was the big difference memory-wise between these three? See if everyone remembers.
When they collide, it's bad things.
When which two collide? Any of them?
The heap and the stack.
Yeah, bad things happen. What happens?
Sadness occurs.
Sadness occurs. It's true, sadness does occur. But what specifically happens?
It stops running.
It stops. Why did it stop running?
Because there's no memory left.
There's no more memory. There we go.
Because the heap's on the bottom and the stack's on top.
Right.
It starts to eat into each other.
Sure. Although if we're in C++ and the stack grows into the heap, do you think it would stop?
No.
Never.
No.
Nope. Yeah, it wouldn't. If you couldn't allocate memory from the heap, would C++ stop you? No. You gotta check for that
More
manually.
sadness.
Yeah, you have to check for that manually. Your program's not going to stop. And more sadness. Yep, that's how we roll. Okay, and actually, memory-wise, morning.
Story time.
The side.
It's your story.
Do you want a real story or do you want like?
Funny story.
One, it's
Amazing.
short, sweet, to the point, either real or funny. I don't actually I prefer funny. But go ahead.
Adventure.
Yeah.
Um,
Well, if the real one is funny, that would too.
I don't know, man. I ran into Bowser on my way here.
Bowser.
Yeah.
Now, which version?
Yeah, it's like 50.
Was it skeletal Bowser or,
I ran
giant
into
one or?
the original Bowser.
Oh, the original one.
Yeah, you know he's.
So you had to run and get to that axe and
Yeah.
cut the bridge down and send him into the pool
Yeah.
Yeah,
pit.
of course.
Now, did you rebuild the bridge afterwards so other people wouldn't fall in?
Oh no, I know how to swim. So. I
In
just-
lava?
In lava?
Oh no. You know
No, he has magical powers, so he won't burn.
Oh, okay,
so
all right,
he
that's
doesn't
good.
care.
Good. All right, back to class. So between the stack and the heap, how is the stack allocated?
Yes.
Yes. It depends.
It depends. Oh, no, there's a specific way the stack is allocated.
Oh, this
Dang
Dang
it.
it.
Good try.
My
good
go-to
try.
answer.
Hmm? How,
22.
how does it grow
with the program.
with the program? Does it grow, allocate anywhere in memory or a specific way?
it's like.
In order.
In order, right. It's on
Top to
top and then
bottom.
deallocates at the end. So it's always growing and shrinking at the end. How about the heap?
Just,
Anywhere?
Keeps growing.
Well, grow. It's not so much that it grows; it just allocates
It
wherever.
just sits there.
What can happen memory-wise? What could happen to the heap that could not happen to the stack?
Stack overflow. Well, no.
No.
That could happen in both. You could be heap overflow, so to speak.
The heap
That
has
goes
gaps.
The heap can have gaps.
Oh, yeah.
Everyone see that or understand?
Yep.
We'll do a quick picture for the kids at home. For the students at home. Diagram. Let's do it with the diagram.
Yes. Draw.
Don't forget to mention the glare.
Oh yeah, the glare.
Show us your artistic skills. What?
Right there.
Oh yeah.
Oh, that was really bad.
Oh man.
There we go.
There you go.
We'll get it eventually. All right. So just keep in mind that in memory, we're going to see this picture. This marker is terrible. I'm going to totally miss it. Oh,
you
almost off.
that bouncing.
That would have been awesome.
That was almost really cool.
There we go.
Failed. Just like
So what's on top?
Static.
Static.
nothing.
Nothing. What's usually in static?
The variables.
Which variables?
The world variables.
World variables. I like that. We should call them world variables. I like it. But they're called global variables.
Same thing. Globe, world, whatever.
All right, what else is up there?
Um,
Let me make this picture a little clearer.
Good question.
That's a great question. By the way, that word is called static, in case you can't read it. What else is up there? What else is known when your program begins?
Runtime?
Runtime. Well, no, your runtime is during the execution. But what else is static? You have your global variables and your
Yeah.
int main, which is your
Main function.
your main.
Okay.
You're on the right track. So it's your code. The global variables and of course the code
Oh.
is also inside of here. Now there's actually a bunch of other stuff as well, but you'll learn about that in architecture.
Okay.
But for this class, that's all you need to know. What comes after static in general?
The
Stack.
The stack.
In general.
All right, in general. And what's at the bottom?
Heap.
Okay.
Heap pancakes.
So you might have int main right here, and you might, let's see, let's have some function 1, int a, wow, that's bad, int a, and then function 2, which might have a double d, and then call function 1. So then if you have main, and main calls function 2, and it ends, what happens is first main gets allocated. We'll give main a variable, so we'll do it char_c, and then the stack is going to always point to where it begins and then its end, which is here. So that once, that's what happens when execution is essentially right here. And once execution jumps down to function 2, you're going to jump up to function 2 right here. It's going to allocate function 2. Function 2, which also has a double D. And this pointer gets updated to down here. And then once execution goes function 2, down it's going to call function 1. We're up here. And now we have int function 1, which has a what? An int a. All right. Okay. And then when you return, someone needs to tell me that this camera's a little off. Yeah, gotta tell me, guys.
Sorry, I was too
where's
busy
the fun in that?
watching.
Yeah.
There we go. Much
Where
better.
did you go? Like, you were just on a roll.
Well, that's why I say, Dr. Woods, something like that. All right.
Sorry,
It's okay.
neglected our duties.
Now, and that's where we are essentially when execution's right here. Once we return from function 1, this pointer would go up here. Once we return from function 2, the pointer would go up here. And then once int main's done, the pointer goes up here and the program is complete. Okay.
Magic.
It's magic. All right. So let's continue on. Let's see. Stack, simple. Okay, static. Talked about this known, everything that's known prior to execution. So your global variable size, your code size as well. Runtime stack, contiguous memory region. It grows, space is allocated when the activation, okay, the stack frame is pushed. It shrinks when methods terminate or deallocate. This is the example I just put up on the board where first main was allocated, then function 2 was called, so function 2 was allocated with a double D, and then function 1 was called, so then function 1 must be allocated with an integer A. And then once it returns from function 1, this pointer would go up here. Once it returns from function 2, the pointer that was here would go up to here, and then we complete. If after main you had function 1, once the pointer was here, it'd allocate function 1 overriding function 2 at that point. Is that clear, or do you need me to show you how that's done? Nope, great. All right. Heap. So they're allocated and deallocated as the programs run, aka they're not associated with specific events such as function entry or exit. You explicitly specify when you want to allocate something on the heap. What's found on the heap is dependent on your language. In Java, it was always your objects. In C++, it's whatever you want it to be. I think you can you actually allocate functions on the heap? Yeah, you can. I can do it. I know how to do that. I know how to do that in C++. Hopefully you'll never do that. Please don't. But in general, you can.
What's so bad about it?
So you're going to allocate something on the heap and then try to run it, switch execution over to it so you can start running it.
Sadness occurs.
You can do it. And if you have a special program that's trying to dynamically load code, yeah, you could do that. But there's going to be no purpose for that in this class. But you should know that in C or C++. Yeah, sure, you can do that.
Do not do it.
But don't.
Sadness.
Before we go back to the heap, oh yeah, talk a little about my heap. In Java, you use the word new. In C++, you use new and delete. In regular C, it's called malloc and free. So you never had to delete in Java because Java would automatically delete the memory for you or deallocate it for you. In C++, you need to do it yourself, or else you'll start using up memory unneededly. And that's why we learned Valgrind, so we can tell when we haven't deleted something. Or Valgrind. I'm going to do that all semester. All right, so C++ says delete. Other languages, Java, Perl, Python, employ garbage collection tree. Yeah, claim the heap usage. Why would C++ force you to do the garbage collection?
Because that's one of the features of the language.
Features of the, yeah, but why would they choose to do that? Why did they choose to employ a garbage collector like all these other languages do?
Because they weren't fancy like that.
They weren't fancy.
Yeah, maybe they wanted to specify when you want to actually collect your garbage.
Why would they do that?
More flexibility.
So
More
your
flexibility.
program isn't garbage collecting when it's not supposed to be. See, it's a very important.
No, in Java with mark and sweep, they're very good at detecting when that object's gone completely out of scope, so they know when that object is gone, and then they can go in and deallocate it at that point. But flexibility, why would it be more flexible?
Because, like, pretty much and that's been like the concept of C++.
Right, so C++ you can do whatever you want, and that's been really the concept of it behind it. But why would they want you to have that much flexibility?
So that you can create more powerful languages like Python?
Right, so you can create other languages that are very powerful. It also has to deal somewhat with performance, because in Java you have to have this mark and sweep running in the background. C++, you don't have anything running in the background.
So it's faster.
It can be faster, yes, depending on your application. Another reason is that the real reason what it comes down to, it has to do with flexibility, but the point of that is C and C++ were meant to be system languages. And when a system language, aka something that's running, pretty close to your hardware, the kernel, you don't want to have a garbage collector running all the time. That would actually be a huge performance problem at that layer of your software stack. So, for system reasons, they want to have new and delete, and they also want to actually give you the option of not having to allocate memory. All right, here's a picture. Static area, stack grows down, heap grows up. That's the general way it's drawn. You could have it reversed where the heap's on the top and the stack and stack's at the bottom. But I'm going to try and stick with this way of doing it. Stack overflow occurs when the stack meets the heap. So we talked about that briefly. Okay. So new returns the start address of a block K of unused heap storage. All right. So let's go back to our picture and let's change this up a bit. Let's go back to function 1. We'll have, what would be a good one? Here's a good example. Let's do string, and we're going to do 2 examples. str1 equals hello. Where is that allocated in C++? Does anyone know?
Yeah.
That one's actually on the stack. So when you write it like this,
Why?
because you can allocate objects on the stack in C++.
Wait, why is there parentheses?
That's a.
Why is there a parentheses? That's a great question. Who would do that? So then you have str equals hello.
It's okay, we know it goes to the.
So how can you like specify what you want on the stack?
Right, so here it comes. So that's on the stack. Let's do it on the heap now. And I'm using this very loosely. This is not technically correct, but I'm just for clarity at this moment. str2 equals new string, and this needs to be a pointer. Hello. All right. So what this does is now, at this point, when execution's at this point, you actually have str2 equals, actually, what does it equal before it hits the new? What's str2 equal to? What would it be equal to? Ooh.
No.
Maybe.
Pointer.
Huh?
Pointer.
It's a pointer, and what address is contained in it?
Address
The
of
address
the-
of hello to.
So execution's up here. It hasn't hit the new yet.
Oh. To the name. Oh wait, no, you're a good man. Never mind.
Because when the stack is allocated, it allocates the memory for str2, so it has the memory to store a pointer to a string object, but there has to be that has to be equal to something. What is it equal to when the function starts?
Nothing.
It's equal to something.
Random stuff.
Random stuff, exactly.
Is that right?
Yes.
Yes.
You have no idea. Literally, the C++ specification says it is undefined.
Why?
Why would they do that? That's a great question. Why would they do it?
Don't look at me, I'm the one asking the question.
Anyone could?
What I remember from me is this class when, like, I think it's just like, I don't know, it's too much stuff in the memory, so it just like points at anything.
Right, it points to anything. Why would they not initialize it to null? Because that's what Java and other languages will do implicitly, is that it would be null or 0 or something. Why wouldn't they initialize it to 0?
Or you can, when you try to access it, it's null, and that causes a problem.
Well, yeah, but I mean, if I access it right now, who knows what I'm doing? I could be doing anything. Because this could literally be pointing, let me use...
Well, it's not exactly just nothing, I'm sure. It's just like...
Because this str2 could literally be pointing to literally anything in memory. Don't know what. Why wouldn't they zero it out?
I don't know, because if it equals it to null, wouldn't that set null in the heap and like then you have to remove it?
So,
It doesn't have a garbage collector, so.
okay, yeah, there's no garbage collector, so there's no need to do it. That's correct. So there's a cost to initializing things to null. While very minuscule, C and C++ all about performance as well as flexibility. So they literally do not want to take the extra step to initialize it to 0 for the performance cost of that. Yes.
That sounds like a stereotypical programmer right there.
Right. Literally, it's performance. No joke. They don't want to initialize it to 0 because that is a performance hit. Even though it's very small performance hit, that's the reason why. Okay. So, currently it's pointing to who knows where, and I'll draw a little arrow going to don't know. Could be pointing to the kernel, could be pointing to something in heap, could be pointing up here, could be pointing there, could be pointing wherever. So execution's up here. We'll go ahead and jump down to this function, And what happens then is it does actually allocate the string object on the heap.
Why does it allocate it to the heap? Oh, this is a string, so yeah.
No, because we're using the new command.
And
Notice up here, we're allocating the string on the stack. Here's string on the stack. Here's a pointer. Notice that star. That star in front of it in C++ is telling you explicitly that it's a pointer. This is a huge difference than with Java. In C++, if you want a pointer, you put a star in front of it. Therefore, it's now a pointer to a string object. So to me, it's clear what's going on. So I prefer this syntax over the way Java does it. But you put a star, so you're explicitly saying that str2 is a pointer to a string object. Then you allocate the string object with new, put it down here. And then, since you're setting it equal to that new object, we go ahead and have str2 pointing to down here. There we are. Okay? Any questions on that? All right. Let's see. Heap overflow occurs at the same time when you can't allocate any more memory. So, for example, we were over here and we kept allocating heap all the way up to the stack. You'd have a heap overflow out of memory, just like a stack overflow, just on the other side. All right, so now you have delete. In Java, you wouldn't have to delete this string afterwards, but
hand-holding.
huh?
It's hand-holding.
It is hand-holding. But if this program were to execute by itself, when we were done, the stack pointer would be up here. You still have a piece of string memory in heap, and you'd be, that was it.
Kind of question between C++ and Java, kind of going back to the garbage collection with C++. Is it possible for C++ to be faster in terms of the program with the garbage collection, if done correctly when compared to Java?
Oh yeah, definitely. C++, you're free to not use a garbage collector and new and delete everything by yourself, or you're free to actually choose a garbage collector and use that instead.
You can do that.
Yeah, there are plenty of libraries that do garbage collection for you. So you can swap them in and out or not. It's all about flexibility and performance. Okay?
Are we able to use the garbage collection for class? No?
Ooh, that's a good question. Ooh.
If you can-
No. No.
Yeah, I kind of
No.
figured that.
Now you need to go through the pain of learning how to do new and delete and go through Valgrind and decide how to do everything yourself. But
It's already bad enough using Emacs.
huh?
It's already bad enough using
In
Emacs.
Emacs, yeah. All right, so if we were to run this program, you would have memory leak is what it's called, because you're allocating a string and never deallocating it. If you run this program a lot, you'd be filling up the heap, so to speak. Do note that if your program does have a memory leak, once it closes, your operating system actually frees all the memory by itself. But it's important to always delete things, because if you're running a long program and you keep using up memory, you will eventually run out. Eventually. We have a lot nowadays. All right, pointers are the address of something else.
Wow.
Sounds really simple, but in Java, these were taken care of for you. Now you're going to probably go insane with what's going on. Let's go. Oh, yeah. Yeah, pointers. Oh, it's going to get fun. All right, let's do some class code with this one. Pointers. Let's see, gvim pointer.cpp. All right, what do we got? Include iostream int main int argc char star argv.
Do you need to have those parameters?
You do not need to have them, but I highly suggest you write them this way.
Why is that?
Because then, if you ever, it's really convention. By convention, you write your heading this way. If you need to use them, everyone calls it argc and argv. If you don't have them there, they're actually injected in your code anyways. So
So the argv is a pointer.
the argv is a pointer to a pointer to a pointer.
Okay.
It's a pointer to a
So
pointer.
it's like this.
It's a meta pointer, basically.
Well,
I'm not trying to be
I mean,
funny.
you can. I mean, it's a pointer, right? A pointer can literally point to anything. So you give a pointer pointing to a pointer, pointer, blah 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 blah.
That sounds like a linked list.
No, because a linked list points to each pointer points to a node which has a data and then a pointer to another node. A
Okay.
pointer to a pointer is pointing to a pointer.
Yeah.
Woohoo! All right.
That's all we needed to know.
All right. So we'll talk about argv maybe later. Maybe I'll get to it today. So you have int a, and then you could have int a underscore ptr equals the address of a. Oh boy. What did I just do here? Let's find out.
Try to figure out the address.
Equals 10. Let's go a equals, okay. Let's just run this real quick. G++ pointers.cvp and then run it.
Yeah.
All right. It did not like my address of. Oh, because it needs to be a pointer. There we go. Whew. All right, a equals 10. Great. What do you think a underscore pointer is going to be?
10.
Ooh. Nope.
Address?
The address of,
Where the pointer?
Hey.
yeah, so that thing.
Oh, accidentally.
Yeah.
Well, I mean, that's your memory address. This is a 64-bit machine, so you have 64-bit memory address.
That sounds like fun.
Notice when I rerun it, the pointer address changes. That's because every time you run the program, your program's allocating a different part of memory.
Huh.
Ah,
Yeah.
what do you know? What do you know? All right, let's do some other pointer fun. So we have something called dereference. Dereference goes to basically the memory location of that pointer. So if you dereference a pointer, what's going to be the value?
10.
Everyone see that?
Now I see where you, okay. Now I get it.
It's now 10. Okay. So what if we set what a is pointing to 20, and then we print out what a equals? What is a going to equal at that point?
The memory. Oh no.
So I'm going to
It's gonna
deallocate a pointer. I need to stop pointing to the screen. I'm going to deallocate the a pointer and set whatever that a is pointing to 20.
It'll still be 10.
What is a going to be?
10.
You say 10? Ooh.
Still be low.
Nope, 20.
20.
Why?
Why is it 20? That's a great question. Well, a pointer is pointing to where a is located. So if you were to deallocate what a pointer is, that is a. That is a, because I have it pointing to the address of a. So then if you set what a pointer is pointing to 20, you're also setting what a is pointing to.
So it's kind of like the reverse, basically.
Kind of it's going around, right?
Okay, I see what you're saying.
So, okay. All right. Let me put this in a function. I'll go void pointer1. Whoops, hold on a second. Let me take this, go to the end. We'll take that, paste it right there, and then we'll call pointer1. We're going to recompile just to show you it's still doing the same thing. Great. All right, what is going on here? Crazy professor. All right.
Pretty code. It's pretty code.
It's pretty code. All right, let's go get rid of this. Hope y'all didn't need this. If you did, well, it'll be put up on YouTube soon. So what do I have here? I have,
Sadness?
no I don't, I have happiness. Oh, this is awesome. I have int a equals to 10, and a, I'm calling it pointer, equals to the address of a, and then I have, I'm just going to say print a, forget this. Forget printing. I don't want to type all that out.
See ya.
Type?
No. Handwriting. My hand hurts. And then I have a underscore PTR equals to 20. Then we're going to end. Okay, great. Let's draw our memory out. Wow, that was terribly skinny memory. There we go. You have your static up here. We don't care anymore. You have your stack. You have your heap down here, but we're not talking about the heap, so blah. All right, we'll see the static ends there, so you have stack points there. We'll just ... pointer 1. What's allocated in pointer 1? See if we can get this correct. First off, the memory for the function is always allocated. So there's some memory for the function. Just need to know that. What else is allocated for the memory with the function? What 2 things? Is that clear up there? Good.
I don't know. You said, okay, can you repeat that?
Sure. So pointer 1, we're on the stack. The stack is going to allocate memory for pointer 1. There's the pointer 1 heading, which is right now just pointer 1 with nothing to it. What else is allocated besides that function heading? That's stored on the stack. Two other things. Right, so we have A. So you have int A equals to 10. Great. What's the other thing?
The APR goes to the heap.
Hang on. Then we have int A underscore pointer, which
Randomness.
at first, when the execution is right here, it allocates the memory for it, but it actually doesn't even set A to 10. It sets A to unknown and A pointer to unknown. That's technically what C++ is doing. When your execution's at this line, it sets A equal to 10. So then A is 10. And then when execution is right here, what's A pointer going to point to?
Heap? No.
A, which is on the
Stack that.
right. Could you do this in Java?
Somewhat.
Well, can you point to something on the stack in Java?
I don't think so.
No. No, you can't. But in C++, it's a pointer. You can point to literally anything you want to. You could actually point up to your code as well, if you wanted to. And there's a way to do that, but we're not going to talk about that right now. So A pointer is pointing to 10. Okay. And what's this line doing?
Just chilling.
It's just chilling. So we're going to where A pointer is pointing to, and then we're setting that to 10. So what gets changed?
A. The 20? No.
No, the 20 doesn't get changed. The A gets changed from 10 to 20.
My mind just cannot wrap around that the A pointer becomes 10. I don't know why.
No, A pointer.
That's
pointer.
I keep thinking that's 20.
Yeah,
but it
make
really
sure you
should be
can
10.
see, if you can't see it on the board, there's a star right here, which is deallocating the A pointer. Yes.
What happened if you remove the star? Will it change the memory?
Oh, yeah, okay, great. Well, that's a beautiful question. So let's rewind. We'll leave this at 10. A pointer is still pointing up there. We get rid of this A pointer. What's it now going to point to? Now, I'm sorry, we get rid of the star. What's going to happen? What are we changing now?
It's changing where it's pointing to.
Right, where is it pointing to?
Now it's pointing to 20.
20.
Wherever 20 is.
20 is not actually here. It would be in the kernel. So you'd start pointing to, I'm just going to say the kernel. Kernel at byte 20. Should you be overriding the kernel?
No,
No.
That would be a horrible idea. What is the kernel?
The kernel is the first piece of software that runs on the stack between, it goes hardware, kernel, device drivers, system libraries, essentially your program.
Okay.
So the kernel is what's interacting with the hardware, trying to just basically get it to work and present it somewhere useful.
So can you mess up the kernel from what we're doing?
So, that's a great question.
Yes.
In a modern operating system, no. Because it has protections to stop you from doing it. If you were running DOS, yes. It would just let you do it. And it wouldn't stop you. And most old operating systems, it's C. You want to overwrite the kernel? Sure, whatever. You want to overwrite a random portion of the kernel? Sure, whatever. It won't stop you. But your modern operating systems will say segmentation fault. Now, this code right here is perfectly fine because you haven't done anything bad. What would you have to do after this line to do something bad?
Delete the kernel.
Delete the kernel.
If-
Well,
well,
Delete,
what would be the code?
pointer.
Delete the point. Oh, yeah, you could try and delete the pointer. Oh, that'd be interesting. Yeah, so one bad thing you could do, delete a PTR. Whew, that would seg fault. So yeah,
Also-
you could try and do that.
if you did star APTR and then change the 20, would that do something?
You mean afterwards? Yeah, so
Yeah.
down here you put star a underscore PTR equals to
Like 30?
30. Right, now you're trying to overwrite the kernel, whatever's at this memory address, with the integer value of 30. Yeah, that would also be a seg fault. That would be starting to overwrite the kernel. In reality, if you wanted to really mess up and you were doing hacking, it would be a of PTR equals some sequence of instructions. All right.
For telling us that. Just kidding.
Any questions on that? Very important. All right.
I just know that.
Hmm?
I just know that when you do the star, the A pointer equals 20, the A pointer star really becomes 10.
Right. It actually becomes that A, is what it is. That A. You got it. Okay. So that's pointer 1. So that was a fun little memory exercise. Let's see what else we have. Pointers, memory. Oh, good. So here's a good, I guess, chart to help you understand going from Java to C++. So in Java, primitives, you just allocate them on the stack, int A, we call it a day. The heap example, actually this does not exist, but you can do int A equals new int some value. It's actually an array object, but it's an array object wrapping around your primitives. Okay? Go down to classes. Stack example of a class on a Java class on the stack does not exist. You can't do it. So you can never do this in Java. But of course, the heap example, string str equals new string, I'm a string, it allocates the class on the heap like we talked about in Java last semester. So in C, primitive, same thing, int A. Heap example, we create an A is a pointer to an integer, and you create a new int. And now you have a single int out in memory that A is pointing to. All right? Classes. You can do a class by just doing string str. What's the difference here between the class for the stack and the class on the heap? Yes.
For the stack, you're only you don't have the equals having the do string. For the stack, it's only strings. You named it whatever string str. You can name it whatever.
Right. So the difference, literally is the equal new string, equal new class. It just took that and moved it over. What does that imply about the class? What is its lifetime if it's on the stack?
Lives longer than the heap.
It's actually because
No.
it's shorter. Like, it could be whenever you add something over it, automatically it will move up to the next thing in the stack. So
True, but even more importantly, once that function returns, the string is gone. It's deallocated is what happens. The memory still exists, but it's deallocated. You can't access it anymore. Or at least, I should say, you shouldn't access it anymore.
Shouldn't.
Yeah.
Bad idea.
It's a bad idea. So here are the key differences. Notice that in Java you had an array with the solid brackets, but now you're using pointers inside of C. So now we got to get used to this whole pointer or this star notation. Okay, a couple of differences. Java, arrays are always allocated dynamically on the heap, but in C, you can actually create your array on the stack or on the heap, depending on how you want to do it. Dynamically allocated arrays have a storage on the stack, and pointer to the heap block. So anything dynamic still happens the same way I told you last semester. It's just now you have that star in front of it because it's a pointer. So C++, there's different ways to do it. So this is actually going to create 5 integers on the stack. What's this going to create? Oh, here we go.
It's going to create 10 arrays of a 15th length float array.
Right, so it's actually creating a matrix, 10 rows, 15 columns on the stack. So it'll automatically be deallocated once the function returns. And the next line, you have an integer pointer, and it's pointing to 5 integers that are out in memory somewhere. Okay. And Java is a little differently. You use a lot of solid brackets instead. Notice that your 2-dimensional array had to be allocated on the heap. All right, I think we've I showed this a lot. Yeah.
So when you want to allocate a pointer, instead of just having it pointing anywhere, and you actually have a place where you know where you want to put it, can you specify to look to allocate there?
All right, so you do not allocate a pointer. You're always allocating something and then pointing to it. So let's go back to the code. Let's create a pointer to function for fun. I'll just copy pointer 1 so I have something to start with. And I'll give it pointer 2, and then we'll tell it to run pointer 2 as the program. It's going to do the same thing, that's fine. So we'll have int a other ptr equals a ptr. Okay. So A is going to be printed out, the value currently 10. A pointer is going to going to print out the memory address of A. What's other pointer going to be printing out? Is that too hard to see back there?
Yes. Very hard.
Is it because of the lights, or is the font too small?
A little bit of both.
A little bit of both? All right, let's see if I can increase the font size.
Can you make it like Comic Sans?
It's a good question.
Let's not.
I remember there was a way to do it.
What about Papyrus?
Tools, edit, global settings, file settings, color scheme, no. Key map, select font, there we are. Serif a good one? Oh my goodness, let's not do that. I broke it. Is it Sans? Is that the good one? That wasn't much better. Or is there the Courier? Courier was, I remember being nice. There we go. How about that? Better?
Yeah, that can kind of be seen.
All right, so you have A pointing to 10. We're going to create a pointer called A pointer pointing to the memory address of A, where you allocated another pointer to an integer called other pointer. And what are we setting it to?
The location of A pointer.
Not the location of A pointer, but
The memory.
The contents of A pointer?
the what?
The contents of A pointer?
Yes, the contents of A pointer. So other pointer is going to now point, well, it's not pointing to the contents of A pointer, it's going to store the value that's also stored in A pointer. So, it's not a pointer to a pointer.
It can point to the same location as A pointer.
Yes. So A equals 10. A pointer is going to point to the memory location of A. Other pointer is going to point to, whoa, not A pointer, that was bad. Come on, guys, stop me. Other pointer is going to point to,
Whatever A pointer is.
yeah. They're pointing to the same, they contain the same memory address. Because your pointer is just holding a memory address. So A pointer is holding the memory address of A. Other pointer is then going to copy over the memory address that's stored in A into itself. So they're both holding the same memory address. That way when you're down here and you do, whoa, that was bad. Other pointer equal to 20, it's going to set A there as well to 20. Any questions?
So if you changed the A pointer to like 20 or something like that, then the other pointer would also point to 20.
Ooh, no. So we were down here. Well, hold on. It depends on where you do that. And then after here, you have A pointer equal to 20. What's going to happen? A still equal to 10. A pointer is going to now equal 20. Other pointer is going to equal to the...
To 10, because you did it after you assigned it.
It's going to still be the address of A.
Yeah.
So it's going to still be the address of A. Then when you set other, you deallocate or you go to the memory address of other pointer and set it to 20, A is now going to be 20.
Okay.
One second. Wait, we don't want that. We want, there we go. Do it anyways. I cast the value 20 to an integer pointer and store it. So yeah, A pointers, oh, it's going to print out in hex, which is 20. And then other pointer is the memory address of A, and that way you can still store A. If I were to go over here, like we were talking about on the board, and try and do A underscore PTR equals to, I don't know, 0xFF, segmentation fault. These are, wow, excuse me. That's the operating system stopping you from doing something bad. This is bad. All right. Did that answer your question, Eric?
Yeah, kind of. So we can specify a pointer to change the location of another pointer. But say we wanted to make an original pointer that's just pointing to a specific memory address. Can we, like, specify a memory address of which we're pointing it to?
Right. If you want to be explicit, that's right up here. Notice I took 20 and I said A pointer now point to 20. Memory address, memory 20. It's not very useful because you don't know what's at 20, but you can do it just like that.
Okay.
All right. We're doing great. Do you have any other things? Oh yeah, arrays. All right, let's go take this, move it down here. All right. So now int A, we'll have that equals new. We'll call this one an array. Morning. And of how many do you want? 100? Good.
Yes.
Yeah, what else would it be? Okay. This is where things might start getting a little weird. A is equal to 10, because that hasn't changed. ARY is equal to, ooh, what's that equal to? What do you think is going to be printed out? Anyone?
It'll print out the memory location of the array.
Yes, it'll print out the memory location of the array. Of course, you only need one equal sign, otherwise the compiler will have no clue what you're doing. Okay, so the array is located there. Great. Okay. What if I try and print out, I deallocate array? What's going to be there? No, because
Well,
I'm pointing to something. What value is going to be there?
same thing. Well, you deallocate it.
Has it been initialized?
No.
No. So it's going to be
Undefined?
undefined is the word you're looking for. It might be 0. It might not. Right now it's 0. If I ran this enough, it'd eventually be something else. But it's not necessarily 0. Okay. So if I do star array equals 100, and then I print out array, what's going to, if I deallocate array and store 100 where array is pointing to, and then I print out what array is pointing to, what's the value going to be?
The value of 100?
It'll be 100, yeah. Great. 100.
Yay.
What? Now let's get tricky. What if I deallocate array plus 1 and set that equal to 200?
201?
Ooh, what did I just do? What's ARY plus 1? Oh, you don't know this yet. Okay, here we go. Let's take this one step at a time.
Yeah.
Sorry, one step at a time. One step at a time. So ARY, we have that memory address. Let me go ahead and do this. Plus 0. Plus 0. Let me go ahead and run this. Whoa. What did I do? Oh, I don't want to deallocate it. Not deallocate it. There we go. All right. What do you notice about ARY and ARY plus 0?
Whatever context.
Memory rotation.
So this is ARY. It's pointing. It has this memory address. ARY plus 0 has this memory address. They're the same. So they're pointing to the same thing. Okay. What if I do plus 1? What's it going to then equal to?
The next memory address over.
Right. So it'll be the next memory address over, which was 4 bytes over. Why is it 4?
Because that's how many bytes it takes to store something.
Yes.
4 bytes?
It takes 4 bytes to store an integer in C++, at least on a 64-bit machine. To make that clearer, we'll do a size of int equals size of int. Size of int is 4. So to go over 1, adding 1 to the pointer is equivalent to going over 4 bytes. Okay? All right. All right. Okay, so now that we're down here, if we do ARY plus 1, we're going to deallocate what's at ARY plus 1 and set it equal to 200. What are we doing?
We're setting the next memory location, well, 4 bytes over to 200.
To 200. What's that doing, logically in our minds? So that's setting one of the elements of the array, namely the second one. So then we can, if we print out the deallocate that memory location, it's now 200. This notation can get very tricky, or cumbersome, I should say. So the shorthand, which y'all are all used to, is this. Oops. But I want you to see that they are the exact same thing.
Okay, that's why you said technically it's the second
Element,
element in the array that it's changed, or that it's.
Right, because you're adding 1, so you're jumping over 1, which makes it the second
okay,
element.
that makes sense.
All right. Are there any questions on this? If you don't get this, you're going to have tons of problems later on. Because you're going to be running around memory errors left and right. Okay. Got to save that over. What do we have? Java arrays. So we talked about heap. I think I've shown this up on the board. That's great. Garbage collection. C++ doesn't have it. We talked about stack and heap. We talked about memory leak and all right, so what's memory leak? Who can read the board? So what's happening? You're not
Deleting.
Yeah, you're not deleting. And what's a dangling pointer?
It's a pointer that doesn't point to anything.
Yeah, it basically doesn't, well, it points to something, but it doesn't point to something that's been allocated. All right, garbage. We talked about this. Another problem. All right, we talked about terminology. All right, that's enough of this. Okay. So lastly, this program, let's go ahead and run it through Valgrind. Whew.
Gonna get yelled at.
By the Valgrind, please. All right. It says definitely lost 400 bytes in one block. What did we forget to do?
Deallocate.
Great guess. What did we not deallocate?
Something on the top.
The array. Yeah. So we need to go over here and do. So we'll delete it. We'll recompile and run. It's happy, and then we'll Valgrind it, and now we're good to go. Here's a question. What if I do this?
Yeah, it'll give you a problem that the array doesn't exist.
Okay. So you're saying we'll deallocate array. Oh, by the way, wherever array was pointing, just put 200 where it was. Is that a problem?
Yes.
Yes. Why did it not give me an error?
Because it's C++.
Because it's C++. It doesn't care.
Well,
You didn't overwrite the kernel or any type of protected memory, so it's fine. That means,
so that's what it did?
yeah, that's what it did. Now watch this. Here's another problem. So int 100. Oh man. 101. Should we be able to do that?
No.
No, that's fine. Now I'm going to try and show you why this is pure evil. We're going to go up here. I'm going to actually call it evil pointer. Because
Evil.
this really is evil that this happens. All right. Evil pointer. All right, here we go. So int array 100, int array 1. We've talked about a lot of this. So we set array sub, we'll go 1 to 200, array 101 to 200. And we'll also do, but before that we'll have ARY 1. Let's see if I can get this to work. Just 100, 1 to 101, 2. Now this may work or this may not. It depends on how delete works. Array 1 sub, I think it's 1 if I have this correct. Let's see what happens. Nope, it's not going to let me do it. So, yeah, because it didn't allocate it the two-way that I wanted it to, right next to each other. Oh, let's do this instead. Let's see if I can get it to do it. Double free. Double free? Oh, wow. Let's do it this way. Oh, there we go. Got it. Okay. All right. Set some initial values. Notice ARY sub 1 should equal 101. overwriting some memory. This should be 101 because we set error y sub 1 equal to 101, right?
Yeah. I see what you're saying.
But what was it instead?
78.
And did C++ stop you? No.
Is that a buffer overflow?
Buffer overflow. You could call it a buffer overflow, yes, because you went past the array.
Yep.
So this can happen a lot.
That's a great way to hack people too.
Right. Do you see why this is evil? Because it's not telling you if you went out of bounds. And you overwrote something else. Maybe that 101 was important for something else, but now it's a 78. How can you test if this is happening in your program? There we go, Valgrind. When I do Valgrind a.out, it goes, well, you lost a lot of bytes, but it says you have invalid writes of 4. Oh my goodness, you have a lot of invalid writes of 4.
Evil points.
So what does that mean?
Invalid write means that you're writing outside the bounds of the array that you allocated beforehand. That's telling you you're doing this. Stop doing it.
Stop doing it.
It's bad. Bad, 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 bad.
Bam, bam, bam.
Bam, bam, bam. All right. Any questions about this?
How can you do a buffer overflow in Java? I know it's going over.
Buffer overflow in Java. You would have to break outside the Java language and use what's called native code invocation. Any other questions? None? All right, beautiful. I think that's going to be it for pointers, so let's go and stop there.